So I'm just going to go over some of the PCBs I've been designing, management, procuring, producing, manufacturing. This is a tiny LED PCB. It's a double-sided board, but the LEDs themselves are only on one side. So we've got some SMT LEDs. These are 5050s, and these are 2538s or 36s. These are white, warm white, and these are actually amber. Amber is in the higher side of the brightness spectrum, so you don't need too much current to achieve the same brightness as, say, red, for example. We've got a centrally located MCU, very cheap. It's a Taiwanese brand, so it's quite reliable. It's interesting about these, we've got side-mounted SMT LEDs, but these are usually mounted on the board itself, but we're saving a bit of space by mounting it in the thickness of the board. We've gone for a thicker board because of the heat that's going to be subjected to because of the amount of lumens that we're projecting. This is our power in, and we've got some recharge pins here as well, so these are not connected, and we've got some recharge passives going on here as well. This has got a magnetic activation, so by swiping a magnet you'll flick between the set functions, and the reason for that is so the housing doesn't have a button which can compromise the water tightness without any particular cost, and the application could afford having a magnet to hand in a keyring. This has various patterns for flashing the lights. So another board would be this board, which is quite large. This is about what are we, say about 30 centimeters. What's interesting about this board is that these matrix modules are uncommon in the sense that they are larger. Still your 8x8s. They're larger in dimension, and they're also brighter. So there's two reasons why we would have an uncommon source of supply. Compared to the standard supply, we need to specially order these, so the price is a bit higher for that. We've gone for a very small form factor for the PCB itself, and we're using the PCB end here to attach it inside the housing. Actually, this one could be made ever so slightly larger, just so it could slide into an extruded housing. Fixing just at the ends would be a little bit risky. Another interesting point is that this has an IR receiver which is actually pointing through the back of the PCB, and the reason it's done that way is because we don't have any thickness added to the back for that actual common IR receiver, so we're saving about 2 or 3 mil by doing it that way. It's a little bit creative. On the back we've got a series of LED drivers which are fairly common. We've got our SMT components, and this is an STC MCU. It's relatively good pricing. It's also flash based. Flash is now incredibly cheap for your, it's called local brands MCU, so it's the Chinese brand of MCUs or Taiwanese. Here we've got our ISP programming pins, so by making our own connector there we can essentially reprogram the code in there because it's flash to update it if there's any manufacturing problem. There's a beeper here that's a little bit too high in the form factor. There's a slightly different one now, which you can see the difference there between these two. This is a much better one for the form factor. And that's all that's fairly interesting about this PCB. It's a fairly good thickness. PCB thickness does greatly affect the price. Okay, this is another type of PCB. So you've got your standard diodes, which the advantage of diodes is that themselves they're very cheap, but their assembly fee is a little bit higher. The reason you would go for diodes is if you want to diffuse light in a particular way. Compared to SMT LEDs, these are SMT LEDs on the real, they will diffuse light differently depending on the PCB position in the housing. It will also affect the diffusion of light, the angle of light. It's almost a slightly artistic effect that you're looking for in terms of a difference between these two types of LEDs. Back we've got different type of MCU. It's a much smaller form factor. It's a SOC, surface mount, and it's cheaper than your dip mounted chip. We've got a slightly more reliable IR receiver here, smaller form factor buzzer, and we've got our LED driver, which is capable for driving. It's only got a few linkages to drive inside. We also have the pins for reprogramming the MCU, and this way it's slightly harder to program it because these are chopped off pins. We need a special connector to make contact with those pins successfully. Here we've got a top mounted, it's the thickness of these LEDs allow us to mount this connector, so we can, during assembly, we can simply have the battery cables already plugged into the housing, and then for connecting this we can speed this up by simply just push, fit and automatically screw at these points. Although we do have these secondary or soldered power points. This has gone for a slightly thinner board. We've changed the shape of it to shave off a few pennies or cents on the production cost. There's a lot of scope with this board, and it's going to go to SMT version in a couple of days. These SMT LEDs, these are samples from one of my new suppliers based in Shenzhen. They'll come on reels. Now the thing about these LEDs is that there's always a slight difference in terms of what's claimed as the brightness, and the angles are usually fixed to about 120. So depending on the application, we need to test the effect of the brightness versus the angle in terms of the diffused application. So essentially, how does it look inside the screen is going to be applied in. These are quite difficult to mount for prototyping, but for production is extremely quick. So the PCB I just showed you could literally be populated within maybe 20 seconds. But with the old diodes, you're talking about a lot longer, so the assembly fee is a lot higher. These I haven't actually tested yet, but I've got, as an example, I'm looking for the red and amber version, and I'm looking to test diffusion of light and intensity of light, and also the color. So I've gone for a difference between red and amber. These are 50/50s, and what that means is that it's the dimension 50 by 50, so 5 by 5 mil. These are 5/730s, so 5.7 by 3 mil, so 5.7 mil by 3 mil, and etc, etc. 2835s are extremely common. These are 0.2 watts, so this will be quite bright. We can get 15-ish lumens, something up to that, with LEDs of this type. Another type is IR LEDs. So we've got a remote control here with the coin cell receivers mounted to the back of the board. It's a double-sided board, and we're going to be using some conductive, it's called Goldfingers. So much like with this board, with a Goldfinger we can simply connect it to a connector like that, and then we've got power to test it for Q&A before it gets assembled. And the advantage of that is we can actually program some secondary protocols into the microcontroller such that when it's connected via these points, it runs a different program, so your diagnostic program, to verify its function. This is the same. The only difference is that when it makes contact with these standard rubber buttons, it'll activate the functions it's meant to do. The advantage of that is we've got fairly low cost here. We're not actually assembling anything to the board. It's very cheap as well because you've got no extra parts. And these can just be mounted in your housing and essentially as a sub-assembly process, and then just connected that way. We've got it's an IR encoder, and we should have a little connector here really, because this is a little bit picky for assembly, whereas if we had a very small connector there, small form factor connector, we could assemble that using SMT and save a bit of cost as well. This is a standard IR LED. There are some very high brightness LEDs for IR on the market, which will essentially make your signal a lot more stable, a lot less susceptible to white noise, greater distance, and perhaps you could complicate the speed of the signal as well. Alright, so that's been a short review of all these PCBs which are being designed, project managed and put into mass production.